This is the syllabus of fourth paper, Electrodynamics and Plasma Physics. There are 4 units in it. 2 of electrodynamics and other 2 of plasma physics. Text and reference books are given. We start with the first topic, Lorentz transformation and 4 vector. In Lorentz transformation, we have 2 inertial frame of reference, S and S dash. One is at rest, S frame, and the other frame S dash is moving with constant velocity v along the direction of positive x-axis. With respect to frame S. For any point, we have space-time coordinates in frame S as x, y, z and t. 3 space coordinates x, y, z, and 4th time coordinate time t. In S dash frame, moving frame, space-time coordinates of this point are x dash, y dash, z dash and t dash. And these space-time coordinates are related with each other by following 4 equations. These 4 equations, which relates space-time coordinates in 2 frames, are known as Lorentz transformation equation. First is x dash equal to gamma x minus vt. Second is y dash equal to y. Third is z dash equal to z. Fourth is t dash equal to gamma t minus v upon c square x. Here gamma is equal to 1 upon under root 1 minus v square upon c square, and we write the term v upon c as beta. So gamma becomes 1 upon under root 1 minus beta square. You have to remember these 4 equations. There are inverse Lorentz transformation equations in which we can interchange x dash and x, y dash and y, z dash and z, t dash and t, and then we have to write minus v in place of v. So we can write inverse Lorentz transformation equations. Now we come to 4 vector. What is 4 vector? For this we write x equal to x1, y equal to x2, z equal to x3, and ICT equal to x4. And similarly for dash numbers, x dash equal to x1 dash, y dash equal to x2 dash, z dash equal to x3 dash, and ICT dash equal to x4 dash. If we write we make such transformation, then the Lorentz transformation equations can be written as first equation becomes x1 dash equal to gamma x1 plus I gamma beta x4, second x2 dash equal to x2, third x3 dash equal to x3, and fourth x4 dash equal to minus I gamma beta x1 plus gamma x4. In fourth Lorentz transformation equation, we multiply by IC. So in left hand side it become ICT dash, which we write x4 dash. And similarly ICT becomes x4. Now these 4 equations can be written in a single equation in matrix form as this. In left hand side we have a column matrix x1 dash, x2 dash, x3 dash, x4 dash, and in right hand side we have a square matrix multiplied by a column matrix. This equation can be written as in short form x mu dash equal to alpha mu nu x nu. Here x mu dash in left hand side and x nu in right hand side are these column matrices, and alpha mu nu is this square matrix. By this equation we can now define a 4 vector. The set of 4 quantities x mu is a set of 4 quantities x1, x2, x3 and x4. Mu is equal to 1, 2, 3, 4, and similarly nu also equal to 1, 2, 3, 4. The set of 4 quantities x mu with mu equal to 1, 2, 3, 4, that is x1, x2, x3, x4. this set of four quantities x1, x2, x3 and x4 we write by x mu, which transform according to above equation are known as four vector. So the set of four quantities x mu which transform according to this equation x mu dash equal to alpha mu nu x nu is known as four vector. Here alpha mu nu is this square matrix. There is important property of four vector. It can be shown that dot product of x mu with itself, that is x mu square. X mu square is x mu dot x mu. We write it as x mu square. Summation over mu is implied in it. We write summation or not write, it is implied. Summation x mu square, because mu comes two times. X mu square means x mu dot x mu. The index mu appear two times. Which index appear two times, summation for which is implied. So summation x mu square equal to summation x mu dash square. This is an important property of a four vector. First is defining equation of four vector, which transform under Lorentz transformation as x mu dash equal to alpha mu nu x nu. This set of four quantities is known as four vector, and this is important property of a four vector, that summation x mu square equal to summation x mu dash square, yani dot product of x mu with itself remains invariant under Lorentz transformation. Remain invariant under Lorentz transformation means its value is same in both the frames, unprimed frame S and primed frame S dash. In frame S, value is x mu square, and in frame S dash, value is x mu dash square, and summation x mu square equal to summation x mu dash square. Clearly, summation x mu square remains invariant under Lorentz transformation. It can be proved easily. We take right hand side, summation x mu dash square is x1 dash square plus x2 dash square plus x3 dash square plus x4 dash square. Right, put the values of x1 dash, x2 dash, x3 dash and x4 dash from these equations as x1 dash equal to x dash, x2 dash equal to y dash, x3 dash equal to z dash and ICT dash equal to x4 dash. Then we can prove summation x mu square equal to summation x mu dash square. Now there are many four vectors. This x mu is four vector for space and time. Other for vector is for velocity. Position for vector is x mu, four components of which are x, y, z and ICT. For velocity is a for vector defined as u mu equal to dx mu upon d tau. X mu is position for vector and d tau is proper time interval. Proper time interval d tau is time interval in a frame with respect to which body is at rest. And if we take time interval dt in a frame with respect to which frame is moving with velocity v, then proper time interval d tau is related to this time interval dt by this equation: d tau equal to dt under root 1 minus beta square. Here beta is v upon c. So this is the definition of position for velocity u mu equal to dx mu upon d tau. Now we have four components of it. First three components are ui. We put I equal to mu equal to I equal to 1, 2, 3 and get first three components, which are ui equal to dxi upon d tau. We can write it as dxi upon dt into dt upon d tau, multiplying and dividing by dt. And using this relation d tau equal to dt under root 1 minus beta square, we find that ui equal to vi upon under root 1 minus beta square. Here we write vi for dxi upon dt. Fourth component is for mu equal to 4. We have u4 equal to dx4 upon d tau, which can be written as dx4 upon dt into dt upon d tau. Write x4 as ICT and use d tau equal to dt under root 1 minus beta square. We find that the fourth component of this velocity for vector u4 is IC upon under root 1 minus beta square. So velocity for vector u mu have these four components. First three components are vi upon under root 1 minus beta square with I equal to 1, 2, 3 or x, y, z, x, y and z components of velocity. And fourth component is IC upon under root 1 minus beta square. dot product of velocity for vector u mu with itself, that is u mu dot u mu, we write it as u mu square. So u mu square, that is u mu dot u mu, is equal to 1 upon 1 minus beta square into vx square plus vy square plus vz square minus c square upon 1 minus beta square. Vx square plus vy square plus vz square, we put v square in place of this, then u mu square becomes 1 upon 1 minus beta square into v square minus c square. Here we take 1 minus beta square as common, 1 upon 1 minus beta square. Now put beta equal to v upon c, and we find that u mu square equal to minus c square. C is speed of light, so u mu square, that is u mu dot product of u mu with itself, is Lorentz invariant. Its value remains the same in both the frames S and S dash. So this is definition of velocity for vector. Now we come to a question: find Lorentz transformation for differential operators. Hence, show that D'Alembert operator del square is Lorentz invariant. So we have to find Lorentz transformation for differential operators. Differential operators are delta upon delta x, delta upon delta y, delta upon delta z. Partial differentiations with respect to x, y, z, and delta upon delta t, differentiation with respect to t. We consider a function psi, which is a function of x, y, z and t, 3 space coordinates x, y, z, and 4th time t. If psi is a function of x, y, z and t, then delta psi upon delta x dash equal to delta psi upon delta x into delta x upon delta x dash plus delta psi upon delta y into delta y upon delta x dash plus delta psi upon delta z upon delta x dash plus delta psi upon delta t upon delta x dash. Here we differentiate partially psi with respect to x dash. If we differentiate psi with respect to x dash, we write 4 terms in right hand side. In first term we have differentiation of psi with respect to x. In second term we have differentiation with respect to y. In third term with respect to z, and in fourth term differentiation with respect to t. So delta psi upon delta x dash is equal to the sum of these 4 terms. Now we have to find the value of delta x upon delta x dash delta y upon delta x dash, delta z upon delta x dash, and delta t upon delta x dash. Differentiations of x, y, z and t with respect to x dash. For this we use inverse Lorentz transformation, which are x equal to gamma x dash plus vt dash, y equal to y dash, z equal to z dash, and t equal to gamma t dash plus v upon c square x dash. Using these equations, we can find these differentiations of x with respect to x dash, y with respect to x dash, z with respect to x dash, and t with respect to x dash. Delta x upon delta x dash is equal to gamma, delta y upon delta x dash is 0, delta z upon delta x dash is 0, and delta t upon delta x dash equal to gamma v upon c square. Substituting these values, we find this relation: delta psi upon delta x dash equal to gamma delta psi upon delta x plus gamma v upon c square delta psi upon delta t. Gamma is taken as common and we get delta psi upon delta x dash equal to gamma delta psi upon delta x plus v upon c square delta psi upon delta t. If we remove psi on both sides, we find delta upon delta x dash equal to gamma delta upon delta x plus v upon c square delta upon delta t. This is the relation of differential operator delta upon delta x dash in S dash frame with the differential operators delta upon delta x and delta upon delta t. In right hand side, the differential operators are in S frame, and in left hand side it is the differential operator in S dash frame. This is relation for delta upon delta x dash. In a similar manner, we can find expression for delta upon delta y dash and delta upon delta z dash and delta upon delta t dash. The relation for delta upon delta y dash is this: delta upon y dash equal to delta upon delta y. Similarly, relation for z, delta upon delta z dash equal to delta upon delta z, and at last we find relation of delta upon delta t dash. Delta upon delta t dash comes out to be equal to gamma delta upon delta x plus delta upon delta t. Here we must have v with delta upon delta x. Now these are the differential operators. If we differentiate one more times, we find d2 upon dx dash square, d2 upon dy dash square, d2 upon dz square, z dash square, and d2 upon dt dash square. Then D'Alembert operator in S dash frame del dash square is equal to d2 upon dx dash square plus d2 upon dy dash square plus d2 upon dz dash square minus 1 upon c square d2 upon dt dash square. By substituting the values of these differential operators, d2 upon dx dash square, d2 upon dy dash square, d2 upon dz dash square, and d2 upon dt dash square, we find that del dash square D'Alembertian in S dash frame comes out to be d2 by dx square plus d2 by dy square plus d2 by dz square minus 1 upon c square d2 by dt square, which is del square D'Alembertian in S frame. So we can say that D'Alembertian operator del square is Lorentz invariant. So if we want to prove that D'Alembertian operator del square is Lorentz invariant, we have to prove that del dash square is equal to del square. Value of del square is same in frame S and frame S dash. There is another question. So that following are Lorentz invariant. First, x square plus y square plus z square minus c square t square. And second, four-dimensional volume element dx, dy, dz, dt. To prove the first part, we use Lorentz transformation. X dash equal to gamma x minus vt, y dash equal to y, z dash equal to z, t dash equal to gamma t minus v upon c square x. Here gamma is 1 upon under root 1 minus v square upon c square. Now we want to prove that x square plus y square plus z square minus c square t square is Lorentz invariant. Then we write this term in S dash frame. In S dash frame, this term becomes x dash square plus y dash square plus z dash square minus c square t dash square. Substitute the values of x dash, y dash, z dash and t dash from Lorentz transformation equations. We get this relation. Simplifying this square, we find that this comes out to be equal to x square plus y square plus z square minus c square t square. Here we have used gamma equal to 1 upon under root 1 minus v square upon c square. So it is proved that x square plus y square plus z square minus c square t square is Lorentz invariant. To prove second part, that four-dimensional volume element dx, dy, dz, dt is Lorentz invariant. So volume element in S dash frame is dx dash, dy dash, dz dash, dt dash, and dx dash, dy dash, dz dash and dt dash are related by these four equations. First is dx dash equal to dx under root 1 minus v square upon c square. This is known as equation of length contraction. Dy dash equal to dy, dz dash equal to dz and dt dash equal to dt upon under root 1 minus v square upon c square. This is known as time dilation equation. Length contraction equation dx dash equal to dx under root 1 minus v square upon c square relates dx and dx dash. Dx is line element in S frame and dx dash is length element in S dash frame. Similarly, time dilation equation is dt dash equal to dt upon under root 1 minus v square upon c square. Dt is time interval in S frame and dt dash is time interval in S dash frame. Substituting these values in dx dash, dy dash, dz dash, dt dash, we find that this becomes equal to dx, dy, dz, dt. So it is proved that the volume element, four-dimensional volume element dx, dy, dz, dt, it is Lorentz invariant.